Great to see you back. In the previous video, we were looking at the theorem, the famous theorem, which is called Fermat's little theorem, and we defined pseudo-primes and the Carmichael number. In this case, we are going to look into primitive roots and discrete logarithms. Let's have a look at the definition of the primitive roots and discrete logarithms. Now, first of all, I want to say that we already know the concept of logarithms from mathematics, from college algebra, and from calculus. We've been working with logarithms. Logarithms are very interesting. And we can define a logarithm for any number a larger than 1. And we can say that x is a to the power y. And in that case, we can say that y is the logarithm of x, logarithm base a of x. And what we want to do now is also define the logarithms modulo p of integers, with p being a prime. So we saw different bases. We had the 10 base, we had e for the natural logarithm. We can take a base 2. There are different bases that we can consider. Now we're going to define discrete logarithms as a part of this course, or as a part of the number theories. First of all, a primitive root. What is a primitive root? A primitive root modulo a prime p is an integer r in zp such that every non-zero element of zp is a power of r. That's in fact the definition. We will see what that means in reality with an example. The second element, we can define the discrete logarithm. And the discrete logarithm is defined as, let's suppose that p is a prime, r is a primitive root modulo p, and a is an integer between 1 and p minus 1 inclusive. Now, if we look at r to the power e modulus p, and e is between 0 and p minus 1, 0 and p inclusive, we say that e is the discrete logarithm of modulo p to the base r, and we write this as logarithm r of a is equal to e. Now, let's look at the primitive roots. That's the first element we're going to consider. So remember the definition of a primitive root, and we will verify if 2 and 3 are primitive roots modulo 7. So let's first at 2. We can look at all the powers of 2 in Z7. So we have 2 to the power 1 is 2 modulus 7, which is equal to 2. We have 2 to the power 2 is equal to 4 modulus 7, which is then 4. Then we have 2 to the third is 8 modulus 7, which is 1. 2 to the power 4 is 16 modulus 7 is 2. 2 to the fifth is 32 modulus 7, which is again 4. And we find for 2 to the power 6, which is equal to 64 modulus 7, which is equal to 1. Now what we see, we find 1, 2, and 4, but the other numbers, 3, 5, and 6, are missing. This means that 2 is not a primitive root modulo 7. Now when we look at 3, is 3 a primitive root modulo 7? You can stop the video here, you can do the calculations yourself and then verify if this is true. So if you stop the video now and restart it later, that would be great. So let's have a look. I hope you finished the calculations if you didn't do it. So let's just have a look what the conclusion would be. First of all, we can see that when we have the powers of 3 in Z7, we see 3 to the power 1 is 3 modulus 7 is 3. And when we do that for all the different powers from 1 till 6, we see that all those numbers between 1 and p minus 1 are in fact there. And then we can say that 3 is a primitive root modulo 7. 2 is not. 3 is a primitive root. So that's the way to find the primitive roots related to a specific modulo, in this case modulo 7. Now, when we look at the discrete logarithms, let's also look at this to explain it better with a simple exercise. We calculated in the previous exercise, in the previous slide, the powers of 3 modulus 7, and based on this, we want to find the discrete logarithms base 3. Now, because 3 is a primitive root modulo 7, we can find the discrete logarithms in Z7, which are given by the expression log base R A of A is equal E, with E the discrete logarithm of modulo P to the base R, of A modulo P to the base R. Now, when we say in our example R is 3, and A relates to the integers part of Z7, we can find the discrete logarithms on 3 and 5 modulo 7 to the base 3 as log 3 of 3 is 1, because 3 to the power 1 is 3 modulus 7 is equal to 3. The logarithm base 3 of 5 is equal to 5, because 3 to the power 5 is 243 modulus 7, which is equal to 2. So we can do that for all the elements that we considered in the previous exercise. I only took 3 and 5, but we can find it for all these other examples, for all these other powers, of course. Now, this was the last part of this paragraph. We were looking at these roots and the logarithms. In the next paragraph, we will continue in the numbers theory, and we will be looking at the application of congruences. How will we apply those congruences? What are the basic applications, and how will we use them in certain examples? You're doing a great job, and I'm looking forward to seeing you in the next video. Thank you, and bye-bye.